Hey everyone, we're back here on Three Body Problems. I'm Dr. Jeff Silverman, astronomer and now data scientist in San Francisco, California. And I'm joined by Dr. Rachel Livermore out in Melbourne, Australia, another astronomer.
And today we have with us a guest from California, so we're only juggling two time zones today. We have Dr. Calen Henderson, who is a research scientist at IPAC at Caltech. Welcome, Calen.
Thanks. I'm excited. It's gonna be fun.
And today we're going to be talking about microlensing.
So what is this microlensing? So we've talked a little bit about stuff that Rachel works on and Anahita Alavi using the curvature of the light around big clumps and groups of galaxies on a very big scale. Micro, I'm guessing, would imply something on a much smaller scale. So could you tell us a little bit about that? What's doing the bending and what are you looking for?
Yeah, that's a great question. So microlensing itself is kind of unique as far as exoplanet detection techniques go. So in uh, just to give a little bit of background about some of the others, one of the new ones kind of on the block is a technique called direct imaging. And in there, you're actually taking a picture of the planet itself. So it's a direct detection technique. And in both using transit surveys and radial velocity surveys, you're looking at the way that the planet influences its host star. So you can see ways in which the brightness of the host star changes as a function of time, and you can use that to infer the presence of a planet, or over the past couple of years, maybe the presence of many planets in some of these very rich systems, such as the TRAPPIST one, which we've heard a lot about the past year or so. And microlensing is unique as an exoplanet detection technique in that it's actually kind of doubly indirect. So you're using the light from a star to learn about a planet that's orbiting a different star. So you don't see the planet, and you don't actually even see the light from the star that it's orbiting either. So the way it works is you're looking at some distant star, and usually its brightness is kind of roughly constant as a function of time. And then what'll happen, kind of all of the sudden, is that it'll undergo this amplification, so this brightening of this distant background star that we call the source. So it's kind of the flashlight that's illuminating the system that has the planet. And what's happening, the reason that it's getting magnified, is that the gravitational potential, just the mass of this intervening lensing system, so it can be a planet just by itself, we call these free-floating planets, it can be a planet orbiting a star, it can be an isolated star as well, but those just aren't as exciting. And so the mass of this lensing system, planet plus star or planet, is what is actually doing the bending of the light of this background source star. And so it's taking light rays that you wouldn't otherwise see from that distant background star, and it's kind of grabbing them, bending them, as Rachel was saying, into your eye or into the telescope.
Yeah, it is very counterintuitive because we're used to hearing about, you mentioned exoplanets that are detected by transits. So you have a planet that's very close to its star and it's blocking the light. So we can understand very easily how a star will get dimmer if a planet passes in front of it. But in these cases, a planet is passing in front of a star and it gets brighter.
But yeah, it's interesting. One of the other kind of components that also makes it such a powerful technique is, since you're not relying on the light from the star, or even from the planet itself, as you might be in direct imaging surveys, you can detect things that are almost kind of arbitrarily far away. So microlensing, there have been a lot of surveys that have been looking in galaxies outside of our own Milky Way galaxy, trying to find exoplanets. And they haven't found any yet, but especially kind of with next generations of telescopes on the ground and in space, thinking that we might find exoplanets outside of the Milky Way is actually not that crazy. I don't think it's too far off, really.
How much information are you actually able to find about the planets? So you said that you don't see the host stars necessarily, that the planet itself is orbiting, if indeed it's even orbiting a star. So I guess you can't tell whether it's habitable. Can you tell anything about the mass of the planet?
Yeah, that's a good question. So we can figure out the mass of the planet, and we can figure out how far away it is from its host star. But you're right, we cannot measure the radius of the planet, and that also means we can't measure its density, and we're not able to measure really the temperature of the planet either.
So as far as I know, we can't predict which star is going to be microlensed and things like that. So how do you, pick your targets or try to find these things? In other exoplanet methods, you look at the closest stars or very big stars or very small stars, depending on which method you're using. But for microlensing, are you just kind of staring out at the haystack of stars and hoping a needle pops up?
Yeah, that's basically exactly it. I don't think I could put it better. Yeah, to borrow a line from Philip K. Dick, we're playing what I sometimes refer to as the solar lottery. So microlensing events in general, as you say, they're rare, they're unpredictable. It occurs kind of once per million stars per year. And so if you want to find something that's one in a million, what do? If you can't predict it, you look at many, many millions of stars. And so most microlensing surveys are directed toward the center of our Milky Way galaxy, what we call the bulge. And it's the densest stellar region on the sky. So it means stars per unit area is very, very high. And so that allows you to measure the brightness of a lot of stars at a high frequency, um, kind of with as few telescope resources as possible. And so you can try to find a lot of these needles in the haystack. Um, an interesting point there is that there's another space telescope. It's been in operation for, I think, a little over a year. It's called Gaia. And the purpose of the Gaia Space Telescope is to measure the positions and the velocities of about 1% of the galaxy. So that's about 1 billion stars. And one of the things you can do with a lot of this information, so you have what we call kinematics, how fast is everything moving and in what direction, and positional information, where is it in the galaxy, is that you can actually maybe try to think about trying to predict events. And it might not necessarily be probing the exact same populations that current microlensing surveys are sensitive to. A lot of these stars that Gaia is measuring these positions and velocities for are a lot closer to the Earth than the current planets and systems that microlensing is finding. But a very cool thing is, I don't think it's unreasonable to expect that we could kind of do this predictive microlensing in the next couple of years or so, maybe, where with all of this information, we can actually say, I think that star is going to go in front of this other star at this time. And if we point our telescopes to it, who knows? We'll see a microlensing event and maybe we'll see a planet. And the kind of cool thing there, one of the many cool things, is now you're using microlensing to look at actually very nearby stars, on which current surveys don't do, since so many of the stars are in the center of the Milky Way galaxy so far away. And now you have microlensing kind of complementing a lot of these other search techniques that are looking at these closer, brighter stars. So I think there might be, hopefully a new era of microlensing discoveries coming up on the new horizon as well, related to that prediction power.
Well, thanks again, Calen, for chatting with us. This has been great. Keep, looking for those needles in those haystacks.
Yeah, thanks. It was a lot of fun. I'll keep playing the solar lottery, rolling the dice. We'll see.
Cheers.
See you.